everyone, today we're going to do the 2018 WACE. I only have about 2 hours free right now, so I'm going to do hopefully up to section 2, and then when I come back, we'll finish off section 3 and do the marking. So 3 hours, let's go. In acid-base indicators, red and acid, green and base, and yellow and neutral. The indicator was originally in sodium hydroxide, and excess nitric acid was added dropwise, which the following shows the order that would be shown by the indicator. So it would be green because it's basic. So it's just C. Yeah, because it would be yellow, become neutral, and red, become acidic. Which of these statements regarding the systems is true? System 2 reaches equilibrium faster than system 1. It doesn't reach it faster. The greatest ratio of products to reactants occurs in system 2. Because products over reactants, so yes, because our equilibrium constant is greater. Equilibrium 1 equilibrium in system 1 favors reactants more than system 2. That's also true because it's more reactants. So 2 and 3 are correct only. Which of the following has the greatest electrical conductivity? So let's see, our Ka is too low here, so it's not going to be either of them. And here we have more moles per liter, so we're going to have more protons. And since electrical conductivity is just a movement of free ions, it's going to be B. The compound of structural formula below smells like apricots. What is true for this compound? This is a 1, 2, 3, 4, 5 pentyl. So let's get rid of these butanoate. Organic reactants required to synthesize this compound. So we need this. So this is going to be a butanoic acid and a pentanol. Question 5 and 6 refer to the following. When a piece of indium metal, INS, is placed in some acidified dichromate solution, Cr2O7, 2- aqueous, a reaction occurs resulting in indium ions being produced. The equation for this reaction is shown below. EMF for this was found to be 1.75. What is the E0 value for the E0 K? So Cr2O7 2- has a 1.36 voltage. And indium solid. So then indium solid must be here. And it must be becoming aqueous going this way. And using a clockwise rule, it's going to be going this way if it's spontaneous. So we know that E0 cell equal to our indium is being oxidized is EOX minus, it's E reduction minus EOX. So 1.7 is equal to 1.36 minus EOX. So our EOX is going to be equal to negative 0.34 volts, so A. According to the standard reduction potential, which of the following sets of metals cannot be oxidized by indium metal under standard conditions? So if they're going to be oxidized, they need to be lower. They need to have an E0 lower than 0.34. So let's see, where's Sn? Sn cannot, so it must be B. Let me check. Mg has negative 2.36. Na is negative 2.71. Ca is negative 2.87, and Sr is negative 2.9. Yeah, because Sn is in all of them except for B, so it should be B. Cannot be oxidized. So they'll be oxidized. It must be the below because indium is being reduced. Molybdenum, MO, is present in each of the following species, which are the increasing oxidation number. Okay, so let's see, this is -2, so all of this is -8. This is +1, and we wanted to get to -2. So that's -7, so we need this to be +5. This is -2, so the total is -4, so this is +4. And this is -2, so in total this is -14. So to get this to -12, we need that to be 6. So here this is 6, 5, that's not it. This is 6 again, but this is 4, 5, and 6, so it must be D. Let's just check all are working. -2, so the total is -4, and our charge is 0. Total here is -8 plus 1 is -7. I want to get it to -2, so I do +5. Here is -14. I wanted to get to -2, so I need a +12, so +6. Yep, D. Consider the hydrolysis equation below. Which of the following are conjugate acid-base pairs? They differ by 1 H, so that's not 1. This is 1, this is 1, that's not 1. So just 2 and 3 only. Which of the following statements about the protein databank is/are correct? Allows you to select the protein, then view its structure. Update regularly and accessed by scientists worldwide is free. Is a worldwide repository of all chemical substances listed in chronological? No. So 1 and 2 only. Because it only stores them about proteins, obviously. And they're not in chronological order. Which of the following is not a use of PTFE? Oh no! This is my Teflon. It's in cookware, so that is 1. Windscreen wiper blades, that would be 1 because it's got the low friction. Now let's see, fabric and carpet protection, and parachute canopies. I can see why it would be for C, because you need the low friction so it doesn't like scuff up your carpet and fabrics, I think. I'm gonna say B. Could be C though, because I know that I was literally just reading this right before, because again, for these exams, one of the things I've been working on is the polymers. And for Teflon, I know that it's strong, it's durable. So that could be B. It's also flame resistant, so it could be B. Not sure. Is it in windscreen wiper blades? For its low friction? It might even be A. I definitely know it's D. It's not a use of Teflon. I'm going to leave it as B for now. Which of the following molecules is capable of demonstrating isomerism? I guess the easiest way is to just draw these out. So this is BR, C, C, C. So it's not A. I think it's going to be B because we see it's going to have a H, and then a C and a C. All the rest, BR, H, BR2, so BR, yeah, it's not that one. C2, and that's just alkane, so it's definitely B. The photographs show a class A burette before and after a titration. Using this photograph to determine the titer volume used in this titration. Titer volume. Okay, so the smallest increment we can see is 0.1. So our measurements, or our uncertainty, will be half of that. And then, let's see, it's gonna be, well, they're both 25.33. So this is 5.1. And this is 31.7 minus 5.1. This is 31. This is 30.2 minus 2.3 minus 4.9, 5.4. I'm pretty sure you don't go to the second decimal place because you don't have enough. You can't say that for certain. So it's going to be that, and it's going to be half of the smallest increment. So yeah. So this would probably be 4.9 and 30.3. And that gives me about, I got 25.4. So I guess you could say 25.3. 25.33. Yeah, I'm pretty certain you don't go beyond that. So yeah. The table shows the volumes added from a burette during a titration. What values should be used in the titration calculations? So they need to be within 0.2 of each other. I think I've actually seen this question because someone asked this question before. So the only one that's not within that is going to be 1. So otherwise we add these all up. 19.94, 19.98, 19.94, 20.02, 19.94 divided by 5. 19.96. So D. Unfortunately, I think that is the answer that I remember. Question 14. Group size to investigate the reactivity of 4 different transition metals: rhenium, vanadium, zirconium, and tantalum. It is by placing small pieces of each metal in separate test tubes with the appropriate test solutions. The 1 molar test solutions were prepared by dissolving the nitrate salt of each metal in distilled water. The results summarized in the table below. So these guys would be the ones that are, so these guys are going to be, if there's a reaction, they're going to be getting reduced. So these guys are going to be the ones getting oxidized. So the one where the reaction occurs the most, zirconium, is going to be the one where oxidation happens the most. Because these are solid, small pieces of metal. And then the metal ions will be getting reduced. And since zirconium is the only one where the reaction happens all the time, it's going to be the most easily oxidized. It's the weakest reducing agent, so oxidized least, and that's going to be rhenium. Yes, because it's making these aqueous ions get reduced. So it itself has to be getting oxidized. And the weakest one is going to be rhenium, because none of them react with rhenium. Chemists must act ethically when conducting research with the following statements release their ethical behavior. Not one. Let's give due credit. Yep. Record their experience accurately about altercation to fit their prediction. I think that's one. Chemists dispose of their waste carefully, especially those containing that. Chemists ensure there is only one independent variable in every experiment they perform. That is not one. Chemists declare any conflict of interest relevant to their investigation. So 1, 3, 4, and 6 is only C. Proteins can contain alpha helixes and or beta plated sheets. The intermediate forces holding these structures in their shapes are hydrogen bonds. Which of the following test of equations corresponds correctly to the acid-base theory of the chemists who proposed it? So Arrhenius predicted that they produce H plus or OH. Dissociate. And then Bronsted and Laurie predicted. I have no idea who Davy is, I'm gonna be honest. That one will donate and one will accept, so it's not A, because that is not Bronsted and Laurie. H minus. Dissociated water. I think it's gonna be B. Because here we're not producing OH or H. We're making H3O plus though. This is a tough one. So Bronsted and Laurie, they donate and we will accept. So here for B, this one's accepting and this one's donating, so that's all good. This one's accepting, that one's donating. Here one is accepting, one is donating. And for Arrhenius, we want to make OH. Disassociating in water. So that reacts with water to ionize. But it itself has to ionize, right? So I think it was going to be D. Because D is the only one where it itself like dissociates or ionizes. And then Davy, I just have no idea what Davy is about. Okay, next page. Question 19. Ethanol can be synthesized by combining sugar, a suitable enzyme, and water. The equation for this is shown below. The process is known as fermentation. Which of these shows the effect of an enzyme on this reaction? All the other conditions are constant. So no enzyme present. This is an exothermic reaction. So it cannot be C or D because those are endothermic. And then when there's an enzyme present, our activation energy is going to decrease. Yes. Enzyme present, activation energy decreases. Ethanol can be produced by reacting ethene with steam. The equation for this is known as a hydration. It's shown below. Which of these is incorrect? Has higher pressures than fermentation. Yes. The hydration of ethene is an addition reaction. Yes. Enzymes decrease the activation energy of both the hydration and fermentation. reactions? No, because enzymes only work with the fermentation. The hydration reaction requires high temperatures and fermentation to achieve. Yes. So C is the one. Even though I already crossed this out, I just really want to check that D is also going to be not fit the criteria for the question. Because if it does, then that means I'm thinking about something wrong and I have to go back and check. But yes, hydration does require higher temperatures and higher pressures. Question 21, 22. Ammonia is an industrially important chemical. It is produced on an industrial scale by the Haber process. The reaction of the Haber process is shown below. What is the immediate effect of increasing the temperature and the rate of the forward and reverse reactions in the process? So they will both increase, but since this is an exothermic, so the reverse reaction is gonna increase more. So the reverse reaction increases more than the rate of the forward reaction. So there we go. What combination of temperature and pressure should be used to maximize the yield? So temperature for yield is going to be low, and pressure should be high because it's 4 here and only 2. So low temperature, high pressure. Question 11. The contact process, which is used to produce sulfuric acid, is another industrially important process. The process contains several steps, one of which is the production of sulfur trioxide as shown below. Which statement regarding both the Haber and contact processes is correct? Both are exothermic and both need a suitable catalyst to occur at a satisfactory rate. So both are exothermic, but I'm not sure about the catalyst. I know the contact process needs what do you call it? You need the vanadium catalyst. Both need a suitable catalyst so that the yield of their respective products is maximized. Both can achieve high rates and high yields. That's not true. Does ammonia need a catalyst though? Exothermic and both need a suitable catalyst to occur at a satisfactory rate. I don't think C is a good explanation. I think it's going to be A. Because I just don't think that talking about catalyst and the yield without also talking about reaction rates is like a good explanation. So I'm going to go with A. Soap and water can be used to remove water and oil, grease from skin. The following diagram represents an anion of soap. Which of the following correctly describes the orientation of the circled section and the attractive force it forms? Circled section is towards oil and grease, and the attractive force is dispersion. Which of the following statements pairs can be used to distinguish between an electrolytic and galvanic cell? Distinguish between electric current flows from an external power source. The chemical reaction produces an electric current. It's just A. That does not happen. This does happen though. Ions do not migrate throughout. That's not true. Electrolytic can be used and cannot be used to electroplate. So no. So yeah, it's just A. Okay, section 2. And we did that in, I always try to get my multiple choice done in the 25 minutes, even though it says to get 50 minutes. So now I have more time for the harder questions that we will approach as we go down here. So copper hydroxide is added to carbonic acid solution. writing a balance equation of appropriate state symbols for a reaction that takes place between the copper hydroxide and carbonic acid. So let's see, I'm going to have CuOH2. I'm assuming that's a solid, because it says solid. Oops. So solid plus and carbonic acid solution. So H2CO3 aqueous. I'm going to get that this becomes, looks like it's going to become copper carbonate and 2 waters. So 2H2O liquid plus carbonic acid. Is carbonic acid H2CO3? Yeah, I'm pretty sure it is. Okay. And then let's see, it's copper carbonate. Because my copper is going to solve the H2. I'm just going to see carbonates are insoluble. The only soluble ones are sodium carbonate, potassium carbonate, and ammonium carbonate. So it looks like my copper carbonate is going to be solid. Solid. Predict all visual changes that would be observed, if any, while the reactants are mixed together and afterwards. Oh wait, no, this is a carbonate reaction. That's not an acid. Carbonic acid. Yeah, we have a hydroxide and an acid, so there should be a neutralization reaction. So copper is a blue. So a blue solid mixed with colorless solution. H2CO3 is going to be colorless, water. And then CuCO3, copper 2 carbonate, it's going to become green. Aha, okay, so that's my, so yeah, copper 2 carbonate in my formula data sheet is green. Copper hydroxide is going to be blue. So I'm going to say blue solid dissolves into colorless solution. Green solid appears or precipitates out of solution. Or should I just say forms? Green solid forms from solution. Or forms and precipitates. From solution. From colorless solution. Predict 2 observations that would be different if excess 0.1 hydrochloric acid was used instead of the carbonic acid. Well, one observation would be that, because then you would have, let's just write the equation, CuOH2 plus HCl. It's going to become 2. We're going to have CuCl2 plus 2H2O. Two observations that would be different. Well, CuCl2 is still green. Carbonic acid. CuCl2 is still green. And the blue solid still dissolves. And I still make water. Sure right now. I'm gonna leave that for now. Carbonic acid. I have a feeling that my idea of carbonic acid is wrong. Okay. Say 2 personal safety measures the experimenter should take when conducting these experiments. So we should always wear safety glasses. And we should take care maybe we should say wear protective clothing. Such as gloves. Gloves when handling the chemicals in our solutions. I feel like this might not be carbonic acid. OH. H2O, CO3. You want to make CO2. If I made CO2, I'm going to have a leftover H. Or a leftover O. It's H2. Yeah. Oh well. And okay, I definitely need to come back and do this one. Phosphoric acid is a weak triprotic acid. Write the ionization equation for phosphoric acid, which shows the second proton be released into solution. So that means we've already lost one. So I'm going to have H2PO4, just 1 minus, plus H2O liquid. This is going to be reversible. And then we're going to have HPO4 minus, or 2 minus now. 2 minus aqueous plus H3O plus, and this will be aqueous. Magnesium carbonate is an ingredient of a commonly used antacid. Other than water, list 3 species that will be found in the resulting vessel open to the atmosphere at the completion of the reaction between excess sodium magnesium carbonate and an aqueous solution of phosphoric acid. So let's see, MgCO3 plus H3PO4. So when you get CO2 plus H2O plus Mg2 plus HPO4. So other than water, we're going to have Mg2 plus aqueous. We'll have some HPO4 minus also gonna have, we found in the reacting vessel open to the atmosphere, so if it's open to the atmosphere, then can we count CO2? Probably not, right? Since it's open to the atmosphere. So maybe I'd say PO42 minus. 2 minus aqueous. Or maybe I go, so maybe I go H2PO4. 4 minus aqueous. Because this will react to form the H2. Open to the atmosphere. This is mean because it means I can't say CO2. Okay. Sodium hydroxide solution, NaOH, is used in titration to determine the concentration of phosphoric acid. Other than having a too low monastic, two reasons why the concentration cannot be easily determined by weighing an accurate dissolving in a known volume of distilled water. It is deliquescent, absorbs water from atmosphere, slowly diluting it over time. And then a second reason, wow, this is mean, other than having too low a molar mass. Not readily available in pure form. Wait, is it? I'm not sure if it is. I can't think of another one right now, so I'm gonna say not readily available. Available in pure form. I think it is though. Because I mean, yeah, you have sodium hydroxide tablets. Okay. The table below lists some acid-base indicators and the color that appears over a pH range. Select that will be best suitable for titration between phosphoric acid and sodium hydroxide solution. Justify your choice, including one relevant equation. So it's going to be slightly phosphoric acid is a weak acid. Sodium hydroxide, a strong base. Therefore, resulting pH, salt produced will be basic. Therefore, pH at equivalence point will be greater than 7. It's going to be greater than 7. We'll probably do phenolphthalein. Or phenol, right? Let's do phenolphthalein. So we'll say hence, choose phenolphthalein. ALEIN as indicator range will contain pH at equivalence point. Therefore we'll change color. Near when equivalence point is reached. We can say that a salt produced is going to be NaH2PO4 aqueous, and this plus water is going to give us NaHPO, sorry, just do it like this. Minus will be H3O PO4 aqueous plus OH minus. That's basic. Okay, coming back up to here, not really available pure form. Oh, I'm not sure about that. Okay, I'm gonna have to take a quick break for a second, so I'll be back. Okay, we are back. I just had to say goodbye to someone because I had to get to work. So we'll start the timer again. Okay. Okay, what was it? Was I trying to get back to this again? Hydrochloric acid is used instead of carbonic acid. H2O. Afterwards, carbonic acid, H2O, copper 2 hydroxide, carbonic acid. The blue solid, because Cu is blue, and H, so you get CuCl2, copper 2 chloride is also green, and you're gonna get water. I'm not sure. Okay. I think it's gonna have another one. Gonna have to come back and do that. Example: galvanic cell in the molten carbonate fuel cell, represent the diagram below. So operates hydrogen gas is reacted with the carbonate ion at the anode, while oxygen gas reacts with carbon gas at the cathode. The carbon gas is reused. Okay, I can't see the image, but I should be able to just work it out anyway. Write the half equation, direction in which oxidation occurs. Oxidation is at the anode. So hydrogen gas is reacted with the carbonate ion at the anode. So H2 G plus CO3 2 minus. The anode, I would imagine, this produces H2CO3. No, this probably produces H2O and then CO2. We need CO2 at the cathode. And then oxygen reacts with carbon dioxide gas, and the carbon dioxide gas is reused. So then ox This will be plus 2E minus. So oxidation, I have oxygen. Oh, sorry, no, this would be reduction, because this is the cathode reaction. Plus CO2. What would this be making? With carbon dioxide gas, the cathode. The carbon dioxide gas is reused. Would I have plus 2H plus aqueous plus 2E minus, because then this can make H2O plus carbon dioxide gas is reused. And this can make the CO3 2 minus. Am I cooking? I don't think I'm cooking. I might not use this question if there was information in the image. Actually, here's what I'm gonna do. I'm gonna pull up an image of a molten carbonate cell. I'm gonna see what it looks like. So carbonate ions go from the cathode to the anode. So they are being produced at the cathode. So I think I'm onto something. So they're produced at the cathode. So 40 minus. So I think this will be it. So then my full equation is going to be, I need two of the top equations. So 2H2 gas plus, I'm going to have 2 CO3 on the right, so CO3 2 minus. And my CO2, I'm going to have an O2 plus 2H plus aqueous, which will produce to the top. 2, I'm going to have 3H2O and no CO2, and that's it. How many oxygens do I have? I have 5 oxygens. That's not right. Oh, because I need plus CO2 gas. And then I have the 1 carbon. Okay, that all balances out. More environmentally friendly alternative to the internal combustion engine. CO2 gas produced is reused in the fuel cell. And then internal combustion engines, this fuel cell runs on, or does not require fossil fuels to run. The fuel cell does not require fossil fuels to run. only just gases. Only O2, H2, CO3, 2 minus, and some H plus. Okay, 18. How many pages are there? Quite a few, it seems. 43. And where does section 3 start? At page 32. Okay, and we are on. Oh, wait. No, what was I looking at? I was on page 32. No, sorry. So that's on page 28. Oh my god, what is this? Okay. Page 28, and we are on page 22. So we are actually getting quite. Wait. What page are we on? What the heck? 18? Oh, page 18, never mind. So we have 10 pages. Wines and other alcoholic drinks can spoil when the alcohol contain oxidizes to acid. Acidity regulator monosodium citrate. Citrate is often added to drinks to prevent the formation of acetic acid. The monosodium citrate does this by acting as a buffer. The citric acid dihydrogen citrate acid can be prepared for citric acid and monosodium citrate, containing citric acid and monosodium nitrate. Containing citric acid. So we're going to have H2C6H5O7 aqueous minus citric acid what the heck is citric acid? Is that ethanoic acid? It must be ethanoic acid. So plus CH3COOH. So let's see, make sure I got my structure right. CH3COOH, yep. And this is a buffer, so it's reversible both ways. And this becomes CH3CO C6H5O7 aqueous plus CH3COO minus. Oh wait, bro, I'm stupid. Citric acid is this. Oh my god. Read, buddy, read. So this will be plus H3O. And then this would just be H2O. From citric acid is that. Okay. Buffers that contain equal concentration of both components are most effective. This buffer solution, prepared by mixing 100 milliliters of citric acid with 100 milliliters of sodium, has a concentration of 0.2 moles per liter. Calculate the mass of sodium citrate that will be needed to dissolve in 100 milliliters to make the most effective buffer solution. So I want concentration of H2C6H5O7 minus equal to 0.2 moles. Therefore, I'm going to go H265H5O7 minus must equal 0.2 times 0.1. Because we want it in 100 milliliters of distilled water. .02 moles. Now the number of the sodium H2C6H5O7 equals the number of H2 C6H5O7 minus 0.02 moles, and then the mass of that H2 C6H5O7 is equal to 22.99 plus 7 hydrogens, 6 carbons, and 7 oxygens equal to 22.99 plus 7 times 1.008 plus 6 times 12.01 plus 7 times 16, 214.106 grams per mole. Therefore, mass of the sodium H2 C6 H5O7 214.106 times 0.02 4.28 grams. How many sig figs am I going to? Oh, actually going to need to be 4. So 4.282 grams. Because here it's going to be 4 sig figs. Okay, page 19. If the citric acid buffer was prepared to a pH of 3.5, what would be the concentration of the hydroxide ion at 25 degrees Celsius? So if H3O plus equals 10 to the negative 3.5, I'll do it this way, yeah. Then 10 to the negative 14 is equal to 10 to the negative 3.5 times concentration of OH. So OH is equal to 10 to the negative 10.5. Maybe I should write here at 25 degrees Celsius. Concentration of H3O plus and the concentration of OH minus must equal 10 to the negative 14. So then negative 3.5, negative 14, so negative 14 minus 3.5, so negative 10.5. So 10 to the power of negative 10.5 is just going to be 3. How many sig figs am I doing here? 25 degrees Celsius, that's 3 sig figs. Or 25.0. 3.16 times 10 to the negative 11 moles. Explain why only a small change in pH is observed in this buffer solution when a small amount of sodium hydroxide solution is added, compared to a buffer adding a small similar amount to a system that is not buffer solution. Buffer equilibrium in part A. Okay. At A. Oh wait. This is wrong. This should be aqueous and this should be a positive. So as NaOH or aqueous added to buffer, OH minus increase, which will decrease the concentration of H3O plus by OH minus plus H aqueous, H3O plus aqueous. This will make 2H2O liquid and by Le Chatelier principle, as H3O plus decreases, equilibrium, no, reaction will, reverse reaction will be favored. As reverse reaction rate will be greater than forward, therefore increase H3O plus back to near previous levels, hence pH barely pH only changes small, has a small change. As concentration of reactant, as less frequent collisions. I'll do it here. Okay, and then for non-buffer solution, there is no mechanism there is no excess H3O plus or other mechanism to remove OH. Therefore, concentration of OH minus increases significantly. Causing H3O plus to drop as it becomes neutralized. Then as pH equals negative log 10 of the concentration of the hydronium, H3O plus drops significantly. Oh, maybe here. I'll say there is no mechanism to replace H3O plus. OH minus increase and H3O plus. There is no mechanism to replace the H3O plus. Therefore, final less than initial or significantly less than initial. It becomes neutralized as pH plus pH increases. We have a large increase. And maybe I should add up here. pH equals a negative log 10 of the concentration of H3O plus. Okay. Increasing the concentration of this buffer solution will increase its buffering capacity. Explain this statement. As concentration increase, there are more molecules of the different species in a given volume. Therefore, it requires more volume of a certain acid, more volume or higher concentration of acid/base to overcome the buffer, or I can withstand more. The buffer can withstand more. Addition of more volume or high concentration of acid/base. Space. As more molecules mean it can partially reverse the impacts of addition of such. Therefore, buffering capacity increase. It can, let's just say neutralize / replace more H3O plus buffer can withstand addition of more volume or higher concentration of acid. As more molecules mean they can neutralize / replace more H3O plus. Therefore, buffering capacity increases. Or maybe we should say buffering capacity refers to the ability to withstand additions of acid / base without altering or without significant changes to pH. Page 20. Polycyclohexane dimethyl terephthalate glycol. What? It's a strong chemically resistant polymer that is food safe. Terephthalic acid, and that Build a structural formula drawing state showing 2 repeating units. So here, I'm gonna have the C O and benzene CO. And here phenic acid. Oh, okay. So here they only lose the H because that's the acid, and this one will lose the full OH. So we have the O still, and then the C, the polyester. O C H H, and it wants 2 repeating units, so that's 1 monomer. So we need another 2 of these. C O C O C H H O C H H. Boom. Like that. Looks all good. State on name. The formula of the byproduct. The byproduct is just water. Following shows some of the steps needed to synthesize. Name 2 reagents that we use to synthesize C from B in step 3. Oh, okay, so this is the oxidation because we're changing this aldehyde to carboxylic acid. So you could use acidified dichromate solution or acidified permanganate solution. Permanganate by a balanced half equation showing B reacting to form C. So B is H3C. H3C. Can I just do like C6H6? So let's see, H36 C and then C6H6. So that's C7 H9 CHO. And then balanced half equation, this is oxidation. So this is going to become like that. Oh wait, I need water. And then we're going to have C7H9COOH plus 2H plus 2E minus. Since that's the only thing that changes, I just added oxygen. H3, and then the 6, and then the 7. Yep. Okay, I'm happy with that. 22. Arsenic acid is a weak triprotic acid that can be produced from the element directly through a reaction of water and ozone. This reaction can be represented by the equilibrium constants Kc. See our products. They are both either an aqueous or a gas, so we can write them both. So H3ASO4, we need to be squared, times O2. That's the power 5 all over. We don't include water or the arsenic, so we only need to include the ozone. O3 to the power 5. Then the arsenate ion, I'm gonna have a drink for a second. Is an A aphotic mean amphoteric, meaning it can act as an acid and as a base. With the equation, describe the amphotic nature in this aqueous solution. Act as a base and acid, so that H. So we'll say acid, and let's say plus H2O, liquid, and then if this is an acid, it's going to donate its proton, so that's going to be 3 minus H3O plus. Acts as an acid. As it donates its proton to a H2O, and then for the base we'll say base, and then again HAsO4 2 minus plus H2O, and then H2 ASO4 minus aqueous plus OH minus acts as a base as it accepts a proton from H2O. State why an aqueous solution is found to have a pH greater than 7 at 25 degrees Celsius. pH greater than 7. Degrees Celsius. So pH greater than 7 means that it's basic. Well, I have no information that will tell me that. Maybe I'll say that Kb greater than Ka, therefore the hydroxide ion will be greater than the hydronium ion. Therefore, basic solution. Alright, and H3O plus decrease, thus pH increase. So then pH is greater than 7. Basic solution. This isn't a good question though, I don't think, because it doesn't tell me what it is at 25 degrees Celsius. Ion. Okay, 23. Many marine animals have shells that consist mainly of calcium carbonate. These shells are built from dissolved calcium and carbonate ions. As the amount of atmospheric carbon dioxide increases, more carbon dioxide dissolves in the ocean. There is increased concern that as more carbon dioxide dissolves, it will be more difficult for calcium carbonate to form. Use the following explanations why increasing concentration of atmospheric carbon dioxide decrease the formation of calcium carbonate. So then as CO2 gas increase, we have that the CO2 aqueous will also increase. Therefore, equation 2 will shift to the right by the Chatelier's principle. By LCP, equation 1 will shift right. So when equation 2 shifts right by LCP, we have that therefore CO3 2 minus will decrease. Therefore in equation 3, as CO3 2 minus decreases, be less frequent reactant collisions. Therefore, decreased formation of CaCO3. Decrease the formation of calcium carbonate. As reaction rate or forward decrease. Equation 3 also, should I talk about, yeah, equation 3 will shift to left, therefore CaCO3 will decrease. Less abundant. So I kind of have like a full net where I talk about this and less full reaction rate, and also this. Shift to right. It's reactant collisions. More frequent. Therefore, the forward reaction rate greater than reverse. Okay, page 24. Consider the compounds and their properties listed in the table below. Given that the molecular formula indicates the compounds contain the same number of carbon atoms and therefore only the number of 1 or 2 oxygen atoms or hydrogen or oxygen atoms, propose a hypothesis for why there is variation in the boiling points of these compounds. Boiling point of these compounds. Propose a hypothesis. Maybe I should say as the number of hydrogen or oxygen molecules increase. We have a minus variation. I have to propose a hypothesis. compound. The respective boiling point of that compound will also increase. I think they're the hypothesis. Wait, it says for Y. What's this? Number of molecules. For larger and structures that have stronger intermolecular forces between themselves. Therefore, boiling point increase. Has energy to overcome IMF. Will also increase. Okay, page 25. Explain why these organic compounds have very different solubilities in water. Butanone, so butane, similar molar masses. We all experience similar strength dispersion forces. Then butan-1-ol and butanone. So butane will only experience butan-1-ol. Can I not go back? Oh, couldn't go backwards there. Butan-1-ol and butanone will experience dispersion forces. My mom just came into the room. Where was I? Only experience dispersion forces or butan-1-ol, butan-one experience dispersion forces, dipole. Forces and hydrogen bonding. Water is a polar solvent and experiences dispersion, dipole, hydrogen bonding. Bonding between itself. As butane 1-ol and butanone can H bond with water, the energy released in the formation of solute solvent intermolecular forces is sufficient to overcome and greater than solute overcome IMF between solute molecules and solute solvent and is greater than energy released between butane and water's dispersion force formation. However, butane 1-ol has stronger H bonding than butane 1-ol, more H bonding sites. Therefore, sum of IMF and energy released between it and water is greater than butanone. Released between it and water is greater than butanone. Therefore, more soluble than water and butanone. I'll say therefore soluble here and it's greater, therefore they are both more soluble than butane. IMF formation. Greater butane. Hence butane 1-ol or butane 1-ol is greater than butanone, which is greater than butane. Yeah, what a snowfest. There's another organic compound that contains 4 carbons in each. It's a colorless liquid. Complete below to describe the chemical test used to distinguish between butane 1O. Excuse me. Wait. Butanone is an aldehyde. So it's going to be something like this. I think. 1, 2, 3, 4. Yes, so it can hydrogen bond to there. Okay. I remember I made that mistake last time. Complete the table attached between butane 1 and butanoic acid. So we can use acidified dichromate solution. Acidified dichromate solution. For butane 1O, where's dichromate? Orange solution. Turns green. See how it turns deep green. And then here, orange solution stays orange. You could, I think, also talk about adding a carbonate. And say that the butanoic acid would have effervescence, but the butane 1O wouldn't. Because I think I've seen this question before. Our teacher has given it to us. Question 27. For the molecular form of C6H12 or 2 structural isomers, one which can be readily oxidized by an acidified dichromate solution and one which cannot be. So they can be readily oxidized. Let's see. 3, 4, 5, 6. Let's see. I'm going to see if I can just do this. Have an alcohol. So H. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I only have 12 hydrogens. So it looks like I'm going to have to swap some things around. See. Three. I'll do it like this. 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This isn't going to work, chat. Maybe it has to be an aldehyde. Is that what they're looking for? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh yeah, okay. They just wanted an aldehyde. Fair enough. So 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And cannot be readily oxidized. So 1, 2, 3, 4, 5, 6. I just need to be a ketone. H, 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 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And it's start of section 3. So I'm going to pause here. About an hour and 20 minutes. So we're about 10 minutes ahead of schedule, which is always good. So hopefully 94 marks. I remember the last exam, I think it was 99 marks. Or was that one 106? No, I think that might be the 2019 exam that's coming up. I don't know. I think the 2019 exam has 240 marks. But yeah, I'm going to pause my timer here. I'm going to go head out somewhere. And when I come back, we'll finish. So see ya. Welcome back, chat. We are back doing, we finished section 2, or up to section 2 of the 2018 WACE exam, so we're just going to finish section 3 off now. We got 80 minutes, suggested working time is 70 minutes, and the first question here looks like an empirical formula, so hopefully we can get this out in a lot quicker than 16 minutes, so let's get started. Okay, ipromide is used to enhance images produced by medical procedure called a CT scan. Hydrogen, iodine, nitrogen, oxygen. I'll find the molecular formula of that. 5 contains 0.2986 grams of nitrogen. Of iodine is converted to iodine. Is sampled and dissolved in water, and excess is added to the nitrogen. Okay, so let's just work on this first. So in 3.54 gram sample, number of carbon is going to be equal to the number of carbon dioxide, which is going to be equal to 1.72 liters of carbon dioxide gas. So N is equal to PV over RT. So the pressure is 155.3 times, so let's make sure it's PV over RT. N equals PV over RT. Times volume, which is 1.72, all over 8.314 times 273.15 plus 125 equal to, so 155.3 times 1.72, then divide that by 8.314 times 273.15 plus 125. It's going to be equal to 0.0807 moles. So then the mass of carbon is going to be 0.0807 times 12.01. So 0.0807 times 12.01, 0.9692 grams. And then the number of hydrogen is going to be equal to 2 times the number of water. It's going to be equal to 2 times 0.967 over 18.016. So put this in my calculator, 18.016, 0.1073 moles. So the mass of water is going to be equal to 0.1073 times 1.008. 0.1073 times 1.008 is equal to 0.1082 grams. Then we have the mass of nitrogen can be equal to 0.2986 divided by, so what I'm going to do here is I'm going to find the mass of nitrogen per 1 gram of the IOP, and then I'm going to times it by the 3.54. I'm going to bring everything to the 3.54 gram sample. So divided by 5.62 times 3.54, 0.2986 divided by 5.62 times 3.54. So I'm going to get 0.1881 grams. So then I know that my number of nitrogen is going to be equal to 0.1881 over 14.01. Is equal to 0.1881 by 14.01. So it's going to be 0.0134 moles. Now the next bit, this is probably the hardest bit. All the iodine contain, 2 is converted to iodine, iodine, dissolved in water and excess nitrate, and added to precipitate. The iodide is lead 2 iodine. This produced 2.21 grams of lead 2 iodide. So we have PbNO3. So I'm just going to write here on the 2.5 to 3 gram sample. So I'm going to have PbNO3 2 plus, and it was iodide minus, and I'm going to need 2 of these. So that's going to equal PbI2 plus NO3 minus 2 of them. Don't really need to start. I guess I'll do state symbols. So aqueous. It said this was solid. This was aqueous. Okay. And this produced 2.21 grams of lead 2 iodide. So let's find the molar mass of lead iodide, PbI2, because iodide has a -1 charge, correct? So mass of PbI2 is going to be equal to, what's the mass of lead? Lead is number 82 on the periodic table, so 207.2 plus 2 times 126.9 will equal to 207.2 plus 2 times 126.9. It's going to be equal to 461 grams per mole. So then the number of, let's just do this all in one step. The number of I is going to be equal to, number of I is going to be equal to the 2 number of PbI2, be equal to 2 times 2.21 all over 461, which is going to be equal to 2.22 times 2.21 all over that. So I get that 0.0096 moles. So I know that in a 3.54 gram sample, the number of I is going to be equal to this. Again, I'm going to do it per gram. So this was a 2.523 gram sample. And I'm going to multiply this by 3.54. So 0.0096 divided by 2.523 times 3.54. I get 0.0135 moles. So then this is the same as nitrogen, which is looking good, hopefully. And then so I know that the mass of iodine is going to be equal to 0.0135 times 126.9. Equal to 0.35 times 126.9, 1.713 grams. So then here my mass of oxygen is going to be equal to 3.54 minus 1.713. Drew a line there by accident. My mass of nitrogen was 0.1881 minus my mass of hydrogen is 0.1082 minus my mass of carbon was 0.9692. No, actually no, I think this is fine. 3.54. I thought I might be over 1881 minus 0.1082 minus 0.9692. My mass of oxygen is 0.5615 grams. So my number of oxygen is going to be equal to 0.5615 all over 16. It's going to be 0.0351 moles. So then my number of nitrogen leaves, therefore my number of oxygen over number of nitrogen is going to be equal to 0.0351 divided by 0.0134. Ooh, this is not looking good. 2.6. So then my number of carbon over number of nitrogen is going to be equal to, number of carbon is 0.0807 divided by 0.0135. That is 6, or 134. That's 6. Number of hydrogen. As long as the rest are also nice numbers, it should be alright. 0.1073 divided by 0.0135, 134. Yeah, okay, so this is 8. And then my number of iodine is going to be equal to 1. Because that was what? 0.0135, 0.0134. Yeah, 0.0135. So then here, say times 2. Number of oxygen, that's a bit weird. 3.54. 0.181, 1082, 9692, 96, still have a 16. .0, 0.0134, yeah, 2.6, alright, times 2, therefore, empirical formula is going to be, so we're going to have 12 carbons, 16 hydrogens, that's going to become 5 oxygens, 1 iodine, and 1 nitrogen. C-H-I-N-O, okay, I guess I'll do it like this, C-H-I-N-O, 5, and then the molar mass, so C12H16INO, and 5, it's going to be 12 of 12.01 plus 16 of 1.008 plus 126.9 plus nitrogen is 14.01 plus 5 times 16. So 12 times 12.01 plus 16 times 1.008 and 26.9, 14.01, and 5 times 16 is 381.158 grams per mole. And then the mass of the molar mass of IOP is 791, which is not going to be divisible by my answer. It's going to be about 2. Okay. Mass of IOP is going to be 791 point. See, I don't like this because it's not like it's 30 grams per mole off. Grams per mole. 2 mole of C12, H16, IO, and 5. For molecular formula, it's going to be, it's around that, C24, H32, I2, O2, sorry, that should be N05, so N2O10. I'm not sure if I'm very happy with that. PV over RT. 155.3 times 1.72 times 8.314 times 273.15 plus 125. 0.0807. 0.0807 times 12.01. 0.099692. So 2 times 0.967 divided by 18.016 0.73 plus 16.6. 0.1073 times 1.008 should be about that. Mass of nitrogen in the 3.4 gram sample, 0.2986 divided by 5.62 times 3.54, 1.081, so then divide that by 14.01, 0.034 moles, 2 iodines. It's going to be equal to 2 of that, so 207.2 plus 2 times 1, 2 is 6.9, it's 461, and it produces 2.21 times 2 divided by my answer, 2.0096 moles. 0.0096 divided by 2.523. I think I'm about the 16-minute mark. It's 3.54, 0.0135. So 0.0135 times 126.9 is 1.713. 713 is 3.54 minus 1.713. 181, 0.1082, 9692. Yeah. Can't do much else. 0.0351, 34, 26. Yeah, okay. I think that's the best we're gonna get. Let's continue. A scientist was given the task of investigating the concentration of dissolved heavy metals in abandoned open cut mines that had filled with water to create freshwater dams using a map of 180 locations combining abandoned open cut mines and freshwater dams. Scientists decided to randomly select locations to take water samples. Jeffrey water timing was as follows. At depth of 0.5, acidify each sample with a few drops of nitric acid to minimize heavy metal precipitation. For measuring heavy metal concentration, and then calculate the average concentration range using 2 sample algorithms between random systematic error. Systematic error is an error with the procedure or equipment that would consistently affect every sample, every measurement taken. Two samples before measuring heavy. Equipment used to measure heavy concentration. Heavy metal concentration may not be calibrated properly. May not be calibrated properly. Random error is due to the innate randomness of an experiment. Example. samples at a particular location may by nothing else than pure randomness have a higher or lower heavy metal concentration than the rest of the location. Not sure what else like random what other random errors there would be. Yeah, okay, what's going on? Water samples were collected from 49 of the 180 possible locations. Calculate the sample size as a percentage of the testable locations. That's a very odd question to see in chemistry, but I get it. This is 32 sig figs, so I'm going to say 33%. See two reasons why the samples were not located from all locations. Open cut mines may be too dangerous. To access. Located from all locations. And then another reason, accessing all locations would be time could be expensive. And take a lot more time. Predict the effect of using a smaller sample size on the reliability of the overall results. Reliability would decrease due to smaller sample size, but I'll bring out some methods. Theta equals square. No, I'm joking. Not theta, sorry, sigma. And justify my answer. Smaller sample size means less trials, so random error would have a larger effect on final results. On final results, and if more samples were used. On final reliability, and hence, I'll say that here. Hence, lower reliability. Please tell me this is the end of all the scientific stuff. Yes! Oh, never mind. Once the samples had been analyzed, the scientists found that a particular sample location had a high concentration of cadmium-2 ions. The dam from which the sample came is now used as a water source for leisure activities and irrigation of surrounding food crops. Cadmium is known to be harmful to human health. Authorities are concerned that the cadmium could be consumed accidentally by humans at that water source, or they could be exposed to cadmium from crops irrigated by them. After further investigation, the scientists determined that the freshwater dam had a volume of that, the average concentration of that, with an error margin of that. To remove the cadmium-2 ions, phosphate ions could be added to immobilize the cadmium as an insoluble precipitate. The scientists proposed that sodium phosphate could be used to remove the cadmium-2 ions. Calculate the minimum mass of sodium phosphate needed to remove all the cadmium-2 ions from the water, giving a final answer to the appropriate number of significant figures. Assume that there are no species other than cadmium-2 ions present in the dam that react with the phosphate ions. Okay. So let's just get this out of the way first. Sig figs. Looks like we're going to deal with 4. So my final answer needed to be 4 sig figs. Okay. So for minimum mass of Na3PO4, use minimum mass of cadmium-2, which is CD2+. Therefore, assume concentration CD2+ is equal to 0.531 minus 0.091. It's going to be equal to 0.531 minus 0.091, which is 0.4400 milligrams per liter. Oh, okay, wait, hold on, pause chat. I need to put my timer on. Sorry. Oopsie daisies. And put my focus on. Okay, we're back, chat. Okay, so let me think about this. Cadmium-2 ions and phosphate ions. So we are going to have PO4. So we're going to have CD2 plus aqueous plus PO4 3 minus aqueous. And then we want these to precipitate out. So we're going to need, let me just make sure the phosphate. Yeah, okay. So this is going to become CD3 PO4 2 solid. So I'm going to need 3 cadmiums and 2 phosphates. So that's going to be my equation. So, because the sodium phosphate is the only job is to provide the phosphate ions. Okay, minimum mass of sodium phosphate. Yeah, okay. So here, know that, so we can find the mass of cadmium. So the mass of CD2 plus is going to be equal to 1.123 times 10 to the 9 times 0.44. So this is going to give me 123 times 10 to the power of 9 times 0.44. This is 4.9412 times 10 to the power of 6 milligrams. So this is 4.9412 times 10 to the power of 3 grams. So I just have to divide that by power of 10 to the power of 3. 94. Wait, no, sorry, that's towards 10 to the power of 8. And then this is 10 to the power of 5. 3. Let's make it bigger, so small. Yep, grams. And then so my molar mass of CD2 plus cadmium is 112.4 per mole. Therefore, the number of CD2 plus I have is going to be equal to 4.9412 times 10 to the power of 5, 112.4 divided by 112.4. I get that I have 3,996.1 moles. Therefore, and my number of Na3PO4 is going to be equal to the number of just PO43 minus. It's going to be equal to 4396.1 all over 3 times 2, which is 4396.1 divided by 3 times 2, 2930.7 moles. And my mass of Na3PO4 is going to be equal to 3 times 22.99 plus phosphorus is 30.97. 30.97 plus 4 oxygens. So 3 times 22.99 plus 30.97 plus 4 times 16. 163.94 grams per mole. Therefore, mass of Na3PO4 minimum is going to be 163.94 times 2930.7, and this is okay, I'm just making sure that the number of sig figs I need. 4.805 times 10 to the power of 5, 805 grams. Boom. Because of a lower concentration. So lower concentration of cadmium ions means we need less Na3PO4 to react. Yes. Okay. So that's my answer. Gallium is present. Oh wait. I haven't been. I didn't put my timer back. Okay, I'm going to see how long I've been working for, and then I'll come back and I'll take that time away, just so it's fair. So I'll be back. I checked the recording and I was working for about 5.5 minutes, so I took that away from our time. So we're just going to continue from here. Let's go. Gallium is present as gallium-3 oxide. Ga2O3 in the red mud waste from the processing of bauxite. The first step in its recovery from the red mud is the addition of hydrochloric acid, HCl. This is represented by the equation below. Okay. The results in the table show the effect of temperature on the rate of gallium extraction from a red mud sample. Note that all the other reaction conditions were constant. By applying collision theory. So I'm going to do my explanation first. As temp increase, reaction rate of gallium recovery, so reaction rate also increase. This is due to particles having, or say all particles having higher average kinetic energy, therefore have higher velocity, thus higher increased frequency of reactions, higher average kinetic energy, also means larger proportion of reactants or particles. Proportion of particles have minimum activation energy. Energy, and I'll call this EA, to successfully react. So both characteristics mean overall reaction rate, which is R. Reaction rate will increase due to more frequent and successful conditions leading to reactions. So with an appropriate and clearly labeled diagram. So what if I do like increased temp, or let's say moderate temp and then high temp. So high temp, I'm going to see particles. I think I'll just draw this as a straight line, the separating one, just to make it really clear. See particles whizzing around. See like here and here, high velocity particles. And here I'll go these two reacted to like little sparks or something. Particles have minimum EA, so react. And then for moderate temp, I'll say these are like slow particles. Okay, and then so these are particles. Slow speed compared to high temp. Velocity compared to high temp. How am I going to draw two not reacting? Two particles not reacting. Particles not reacting due to not having sufficient energy to overcome activation energy. So they like bounce away. Okay, I think that's a better illustration. This graph shows how the amount of gallium extracted from red mud varies over time at a hydrochloric acid concentration of that. Sketch on the graph that would be obtained if the hydrochloric acid concentration was changed to 2 moles per liter. So again, it would just simply go reach it faster. And reach the maximum. Oh wait, would it go all the way to 100%? Gallium extracted. Okay, it goes to completion. So yeah, it would go to 100%. And it would get there faster. Because I assume it's not 100% for the one already drawn, because it's being limited by the hydrochloric acid. As concentration of HCl increase, concentration of H plus increase, therefore reactant collisions collision frequency increase, therefore forward reaction rate increase, therefore steeper gradient, for percent gallium extracted, and reaches 100%. Does it say here that the gallium doesn't reach 100%? Reaches 100% as sufficient reactants to go to completion. Reaches completed or reaches final percentage extracted sooner due to increased reaction rate. In a laboratory analysis containing was a mix of excess hydrochloric acid, the concentration and the resulting was analyzed in percentage of gallium determined. Using analysis needed to be in excess so that all the gallium would be extracted. Okay, ooh, SpaceX is interesting. American company announced to send human to Mars to explore the planet and establish a colony. One of the challenges of such a mission is to find reliable fuel sources away from Earth. So SpaceX plans to solve this by using the Sabatier reaction equation. For the reaction is that the optimal conditions are that pressure is there and a nickel catalyst. The carbon dioxide will be obtained from the Martian atmosphere and hydrogen from hydrolysis of water extracted from either the Martian subsoil or the atmosphere. The resulting methane could be used as rocket fuel, while the water could be electrolyzed to produce hydrogen and oxygen. The hydrogen fuel could be fed back into the reaction vessel. Oh my god, that's very complicated. Okay, wait, am I behind schedule? I am. Oh god, I'm gonna have to work my butt off. Okay. I wonder how that happened. Usually I'm ahead of schedule. Okay. Of above economic considerations. Explain why the above conditions are considered optimal for Sabatier reaction in response to address any compromises in So as temp increase, velocity of particles and proportion of particles with minimum activation energy increase. Therefore, reaction rate will increase. And however, this is exothermic. As temp increase by the Chatelier's principle, endothermic reaction will be favored. It seems like yield is not that important. Actually, no, yield is pretty important because they want methane, oxygen, and hydrogen. Therefore, as written, reverse reaction will be favored. Therefore, concentration of the products decrease. Hence, yield decrease. Thus, the RR increase, but yield decrease. A compromised temp of 300 to 400 to 400 degrees C is used. To 400 degrees Celsius is used. Wait, hold on, I just realized. Is this the exam where it's like 260 marks? No, there isn't. It's the 2019. I'm still behind. Jeez. Bro, I'm gonna die in the 2019 exam. Where was I? Let's compromise temp is used. And then we'll say as pressure increase. As pressure increase, rate of reaction will increase. So as pressure increase, concentration of products and reactants increase. Therefore, more frequent collisions. Therefore, R of both. Oh, I should probably say this was above as well. Forward and reverse. Reverse. Reactions favored. Increase of forward and reverse. However, let's see, as pressure increases, okay, we will go to the right. So, as gaseous molecules ratio is, was it 5 to 3? 5 to 3. as pressure increase by LCP, forward reaction favored to partially decrease pressure. So then therefore the products increase, hence yield increase. Thus high pressure of 200 to 300 of 200 to 300 kilopascals used to maximize and yield. Higher pressure, not yield. Used as it is more hazardous. Oh, actually, no, economics as too costly, especially running on another planet. Higher temper, particularly higher pressure. Okay, page 36, I have half an hour left. Predict the effects of the following changes on the methane yield in the saboteur. Oh wait, sorry, circle, not cross out. The volume of the reaction vessel is increased. So then my pressure decreased. If my pressure decreased, I want to go to the left, so this would be decrease. Temperatures increased. Temperatures increased. Then I want to take the endothermic route, which is going to be to the left, so decrease. The methane is removed through a special valve as soon as it forms. It's going to be increased then. And then the partial pressure of carbon dioxide is decreased. Partial pressure of that carbon dioxide decrease, we're going to go to the left, because that's going to go down, so that's going to go left. So we're going to go to the left, so that's going to be decrease again. Graphs can be shown to show the effects of the opposed changes of equilibrium systems. The graph shows the effects of some of the changes made to a reacting system in a flexible vessel. Flexible vessel. I haven't two. I'll say pressure of system increase due to a decrease, sudden decrease in volume. Identify the imposed change at each of the times below. So at time, oh wait, oh sorry, T1, I was looking at the wrong thing. T1 is just here, so equilibrium is established. Equilibrium is established. The change imposed was an increase in pressure by decrease in volume of container. And at time 3, a removal of decrease in partial pressure. So decrease in partial pressure of H2O gas by removing some of it from the system. The temperature changes will decrease at T4. So how does it affect all species? Include any changes to scale and continue until a new equilibrium is established. So T4, temperature was decreased. So temperature was decreased, so I want to go to the right. So then my C4 will increase a little bit, and until a new equilibrium is established. Increase there. That means my H2O is going to increase by double the amount. So there. My H2 is going to decrease by a lot. So maybe there. And then my CO2 will decrease by the same amount. Actually, I should get my ruler out for this. So half it down. So about there. I wish you could have been about there. I think that's a good amount. My H2's got to go down a lot more. There. And then all of these will just be nice straight ruled lines. Ooh, that's very ugly. Ooh, that's also very ugly. It's alright. We will deal with it because we are running low on time. I don't think I've ever ran low on time before. Well, if I run low on time, I mean like I might not finish the exam. Page 38. An Atlantic longfin inshore squid is able to blend into its surroundings and seemingly disappear. It does this by using specialized cells. The squid tunes and adapts the reflection of light from these cells by using a class of proteins called reflectins. Very smart. The amino acid sequence of some reflectins from the squid has been characterized. A small sequence from one of the reflectins is shown below. Section showing all hydrogen atoms. Oh my god. Okay. What's TYR? Section. Tyrosine to TYR. So I'm going to have here, I'm going to have N, C, this is going to be an O. I'm going to have CH, H. This is going to be a benzene. Oh god. Let's see if I can fit that here. O and then OH. Sorry, not H there. Should be an O here. H. And then this is an N, and this is a H, and this is a C. And my next one is Val. How do people draw these like nicely? I don't understand. Because mine always look like a bunch of garbage like this. God. Can I make this benzene a bit smaller, please? Let's see. Small benzene. Okay, I guess that works. And then I need a CH3. So H, and C here, H. And the C is there. So the O's there. So this would be an N. This would be a H, C, H, C, O, and then continue there. And then ASN. I'm gonna have CH. So H, C, double bond there, and then H. Okay. Circle one peptide bond that you drew in part A. I remember this peptide bond is just that. 39. The amino acid leucine is found in reflected. Draw the full structure formula of leucine in each of the conditions specified below, showing all hydrogen atoms. If it is acidic conditions, they will gain a H. So let me find my leucine. So low pH acidic, so I'm going to have H3N plus, and everything else will be the same. Full structural formula, brother. Okay, so HNH, that's a positive charge on the nitrogen, and COOH, CH2, H, CH, CH. No. Let me put you on the side. So I can put one here for ease. God, these are like so hard to draw. Okay. And then in basic, we're gonna lose the H from the COH from the carboxylic acid bit. C, so double bond, O negative. And here again, H, C, H, H. Okay, explain why the structure of leucine is pH dependent. I don't know. Leucine can act as a Zwitter ion, having both positive and negative charge, but overall neutral. Depending on pH, there may be excess or deficient H plus, 3O plus, or H plus in the solution. Therefore, leucine may accept or donate H plus depending on pH and the pH H plus concentration. If pH is high, then H plus is low, therefore leucine will donate and lose a H atom. If pH is low and plus is high, so leucine will accept a H plus atom. Okay. Identify the most strongly attached to each other, justify a choice. Consider the following methods found on neighboring protein chains as they come in close. Identify the pair most strongly attached to each other, justify a choice. This would be cysteine and cysteine. Cis and cis. Both contain a sulfur atom in the branches. No, what's it called? Side chains, that is. Therefore, can covalently bond into a disulfide bond, also known as cross-linking. See, leucine. What is met? What is met? Ooh, methyl also has S. Leucine and valthone. Leucine. But actually, it might be cysteine and met. We'll also have stronger dispersion forces than cis, which will have cross-linking as well. As met has a larger side chain than Val and Liu, who only has dispersion forces, so is the weakest. Sum into the molecular forces. Therefore, strongest sum of EMF or stronger IMF K41. Oh god, oh that is bad. That looks like a big question coming up. Question 40. Acetylsalicylic acid and aspirin is used to treat pain and inflammation. Aspirin can be synthesized from salicylic acid, and the process can be represented by the equation below. The synthesis was reacted with excess acetic anhydride to produce what's the percentage yield of this reaction. So let's see the number of salicylic acid is equal to 45 over 138.12.121 is equal to, with my calculator out for this, 45 over 138.121, 0.326 moles. Therefore, aspirin should equal aspirin theoretical max is equal to number of salicylic acid is equal to 0.326 moles, but the number of aspirin actually is equal to 50.2 all over 180.158. I feel like I've seen 180.158 before. 50.2 divided by 180.158. 0.279 moles. I'm going to quickly redo these. 45 by 131. Give it a few more decimal places. moles. 32580 moles. And this is 50.2, 180.158, 278, 864 moles. F4 percentage yield is equal to 0.27864 0.32580 times 100. 27864 divided by 0.3258 times 100. 85.5%, and we want it to 3 sig figs. The student conducts titration to determine the percentage or purity of a sample of salicylic acid that was used in the synthesis of aspirin. Complete the equation between aspirin and sodium hydroxide solution. So NaOH aqueous is going to become, and so this hydrogen is going to disappear. So we're going to have Na plus aqueous plus H2O liquid plus, so we're going to have our benzene ring, so C, 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 C. That is a terrible ring, but I'm running out of time, so I can't be complaining right now. H, H, OH, and then so the yeah, so C, double bond up there, O negative. Okay. Oh, and then just a circle inside here. An amount 3.55. Oh, I just skipped up a few pages. I'm just looking. Okay. An amount 3.55 salicylic acid was dissolved in distilled water and added to 250 volumetric flask, which was filled to the calibration line. 20 ml aliquots of the acid solution were titrated against 0.96 moles. The average titer was 0. Mass, and therefore the percentage purity of the sample. So then the number of NaOH is equal to 0.01845 times 0.966. 0.1845 to 0.0966 is equal to 0.01782 moles. And for number of salicylic in 20 milliliters, it's going to be 0.001782 moles. So then in 250 milliliters, number of salicylic is equal to 0.00178 times 250 over 20. 0.00178 times 250 divided by 20. 0.0223 moles. Now the mass is 138121. Mass of salicylic is equal to 138.121 times 0.0223. So 138.121, 0.0223, 3.08 grams. Therefore, percentage purity 3.08 all over 3.55 times 100 is equal to, how many sig figs do I want? 3 sig figs. So I just put here 3 sig figs. 3.08 divided by 3.55 times 100. 86.8%. Okay. Oh, we are cutting it close. 6 minutes, 6 marks left. So For the conical flask, we'll add in sodium hydroxide solution from the burette. The same number of drops indicator for each titration. Stop the titration at the first sign of the indicator showing a color change. Boom, 3. 3 will be 1. Wash the pipette with distilled water before filling the salicylic solution. 4. Rolling down the sides. The conical flask during the titration. Okay, so 4. So 3 was stopping the titration at the indicator showing a color change. So we're going to get less tighter than we have. So we have less tighter, and our number of salicylic acid will also decrease. Or the concentration of salicylic increase. So that's going to decrease tighter volume as not to endpoint, as reaction not complete to endpoint, or to equivalence to endpoint. Therefore, mole number of salicylic decrease, therefore purity. Yeah, because then you're saying that you need less sodium hydroxide to neutralize all of the salicylic, which means that you're saying that there's less salicylic than there actually is. Endpoint must be permanent. Okay, and then number 4, wash down the pipette with distilled water before filling with salicylic acid solution. This will decrease. Oh no, because then you're saying it's more distilled water, so the salicylic acid solution is going to decrease. Salicylic titrant is going to decrease, therefore tighter NaOH volume decrease, since you're going to need less volume to neutralize all of it. Therefore, moles of salicylic decrease, therefore purity will decrease. Purity or concentration must rinse with salicylic for this titration. Wow, I've never cut it this close before. Barely 2 minutes remaining. Whew, I mean, okay, I'm probably not going to have time to go through much. I think there was one multiple choice. I think it was just this one, number 10. Which of the following is not a use of polytetrafluoroethene? This is Teflon. So cookware is definitely a use. I can see why windscreen wiper blades would be used. Fabric and carpet protection. Okay, the main thing about Teflon is that it's slippery. So do fabric and carpet protections they get slippery? I think they do. If you put like a rug or something over it, you're protecting the carpet, and then underneath it, it shouldn't be like grippy on the carpet. So I think I'm gonna leave my answer as B. Okay, well, there we go. That is a full 3 hours essentially. I've never been so stressed doing a prac exam before. I've never had to cut it that close, so yeah. Alright. Oh, that's going to be end. I'm going to mark this tomorrow because it's 11:40 p.m. right now and I want to go to sleep. So I will see you guys then. Later. Welcome back, chat. We did pretty much the same as our last exam, except that we lost 2 more marks in section 3. So we lost 2 marks in section 1, 7 marks in section 2, and 13 marks in section 3. Whereas last time I think we only lost 11 marks in section 3. So our final percentage is 89.4, which is fine. Obviously I would like it to go up rather than down by 2 marks, but it is, I guess it's, just part of the randomness of the exam. Shows that it was been pretty consistent, so let's go through it. Oh, this was good. Here, I misread, was that it cannot be oxidized. So I actually had to do the opposite of what I did. I had to find the ones that were all above rather than all below. So it would have been D. That was just a silly error by me, not reading properly. And then down here, this was a funny question. You could have chosen any of these and they would have all been right. They were all considered distractors, so they were all correct, which is a bit odd. But this, as soon as I saw the marking here, I realized why. Okay, so it is 0.05 milliliters per burette. And since we're taking 2 measurements, then our final uncertainty will be 0.1. And then from there, you just have to do the calculation yourself. So that will end up being 25.39. Because I think it was like 25.4 when I used my numbers. But yeah, the thing that really should have tipped me off is this. You have to do the uncertainty twice, so you cross out those 2, and this is the only one that's relatively close, so it'll be C. But that was multiple choice done. This one, okay, I read a bit of Humphreys. Humphreys was that when you react an acid with a metal, create hydrogen gas. I think that's the only thing that differentiates the rest of these. I guess you can say that this ammonium doesn't dissociate, so that's not an Arrhenius. And then this one, this Davies, this is not Davies, because Davies is again a hydrogen gas. All the acids and bases react to form salts and water, which are not apparent in B or C. So yeah, I was lucky to get D there. The rest of this was good. Okay, let's move on to section 2. Straight away, this was very sad. Oh yeah, here I gave myself the full marks. However, I probably should have said that final solution was colorless instead of just saying colorless solution over and over again. But I thought, it's colorless solution is right there. So, and I said it throughout the thing, so I gave myself the mark. For C, I thought that the copper chloride would be solid when. So copper chloride can be solid, but if it's put in a solution, it will dissociate into its aqueous ions. So that's when low solid produce occurs. And I could have found that in my solubility table, but I just wasn't checking. So then from there, the solution would be blue because you would have the Cu 2+ ions. You could have also said it occurs faster. I'm not sure that's a different observation, but whatever. And then no gas produced, because this equation here, you could have thought of this as a carbonate equation, which I was a bit surprised at since it's not an acid. But yeah, you could have made that essentially the carbonate equation, and then your products would be like CuCO3 plus the CO2 and water, and then you have to balance it obviously. So then from there, gas produced. And then of course, that means that for up here you could have said bubbles or effervescence. And down here, this was so silly. No, it was literally in the marking key. It said to not award marks for not available in pure form. So obviously I couldn't award myself marks there. However, what I really needed to say was purity not known, because for sodium hydroxide you can get it in pure form, the pellets, but you can get it without the no impurity. I'm not sure. But you could have also said that it absorbs CO2 from the atmosphere to form sodium carbonate and water. So I'll probably use that for the future when I do these questions and it's sodium hydroxide again, because I think it's usually sodium hydroxide. And then you could have also said it's hygroscopic, which means it absorbs moisture just like being deliquescent, but it doesn't go into solution, so it just changes the mass. I don't think I'll say this because I feel like I'm gonna get hygroscopic and deliquescent mixed up. So I'm probably just gonna say deliquescent because that's easy to remember, and absorbs CO2 from the atmosphere. Then for here, I lost 2 marks because what would happen is that I needed to talk about PO4. I need to say PO4 3 minus aqueous would be at equivalence point. That's because it needs to fully neutralize. So you're gonna have your H3O or H3PO4 aqueous plus 3 NaOH minus. Oh, I should be Na. We'll just do OH. OH minus aqueous. And then this would become your PO4 minus PO4 3 minus aqueous and water. So this is the full equation. Wait, sorry. To balance this a little bit, to move that over. So this would be the equation. So I need to talk about PO4 instead of just this H2PO4. So I lost 2 marks there because I needed to say PO4 would be in the solution, and then my equation needed to be the PO4 one. So yeah. But other than that, it was phenylene. And then I did talk about pH. Must be approximately close. I'll be slightly basic. One, two, three, four, five. Oh, I just realized there's 6 things you need to talk about. 1, 2, 3, 4, 5, 6. But there's only 5 marks. Okay, another thing I should have talked about is that Na plus ion doesn't hydrolyze with water. Wait, so there's 6 things I needed to talk about, but there's 5 marks. How am I giving myself the marks then? Okay, I'm gonna leave my mark as 3. Okay, but there's 3 things I should have talked about. That's odd. So I got 1 for saying phenylene. I got 1 for saying the solution equivalence point be slightly basic, and I got 1 for saying pH, change approximate the pH of the equivalence point. Okay, well, gonna give myself 3 marks there, but yep. And here, 4 marks. Could have used a bit more better wording to be, if I wanted to be exactly like the marking key. I could have said that it prevents CO2 from entering the atmosphere, and I could have said that fossil fuels are non-renewable, but that it runs on renewable fuel like O2 and H2. So it doesn't really run on these. Those are in the solution, but you don't need to constantly supply them. And down here, bada bing, bada boom. Oh, it was so good marking this. What was this? Oh yeah. In the marking key, it had in brackets that the different species were citric acid citrate. So I think I maybe wanted you to talk about them, but I gave myself the full marks anyway. Other than that, yep. Can withstand more, it can neutralize. I think they also said it can react with more H3O or OH minus. That would look good. But I mean, my neutralizer replacing H3O explanation is also fine. So maybe I would add a note here. Better if react with more H3O plus or OH minus added to solution. when added to solution. And going down. For some reason I drew these as benzene rings, but I mean obviously it's not benzene rings, so that was a minor error. Here I could have said sodium dichromate solution or potassium dichromate solution, but they were in brackets, so again I gave myself the full mark, so I wasn't exactly sure if that was part of the marking key. But just for next time, remember to write sodium or potassium. Oh, what has happened to my gauge? Just lagged for a second. Here, all I really needed to say was this, where the basic equation goes to further extent than the acidic one. Just make sure that's what it was. Reaction 1. Yeah, KB over KA. Full marks. Here, I should have been more specific and said we'll experience these when it's with water, because butane will not experience hydrogen bonding between itself. So I should have been more specific about that. And then I lost a mark for not talking about why butane has low solubility. I think I talked about it only having dispersion forces. Yeah, butane will only experience dispersion forces, but I didn't talk about what that leads to. And it leads to the dispersion between butane and water being not strong enough to overcome the intermolecular forces of water-water, which has dipole and hydrogen bonding, so then it has low solubility. Here again, I should have said sodium or potassium, and instead of saying orange solution stays orange, I could have said no visible reaction. I don't know why I didn't say that. That's like, I don't know, I wrote that so many times in my tests that it should be second nature to me, but I just forgot to say it, I guess. But yeah, no visible reaction. And then this was all good, so we're going to section 3. This was quite sad. I thought that the answer that I got was a bit off, and it was a little bit. So what I needed to do is, if I did, I think if I did this step to more decimal places, I would have got 1.707. Let me see, 0.096 divided 2.523 times 2.54. 0.00136 times 126.9. Yeah, or 1.708. So I should have done this to more decimal places. And this step, and then follow that on. Because then my moles of oxygen will be 2.65 instead of 2.6. Because what they wanted was for you to multiply by 3 instead of by 2. And if you multiply this by 2, you get 5.2, which is 0.2 away from the furthest. And if you multiply by 3, you're going to get 7.8, which is also 0.2 away from it. Yeah, 7.8, which is also 0.2 away from the furthest. So I thought, yeah, whatever, I'll just do point times 2. But it ended up being 2.65, which means if you multiply it by 3, you get a lot closer. Things like 7.95 something. A lot closer to 8 than if you just multiply by 2. So that would lead you on to multiply by 3. And then your empirical formula would be this. But then, what was it? It was that, oh yeah, I also just didn't multiply my iodine or my nitrogen by 2 when I did it, which is quite silly. But then yeah, that would end up being your final molecular formula, because that would be the what do you call it? That would be, sorry, yeah, this was meant to be 8, not 6. I think that was 8. There we go. That was getting bad with you. Anyway, but yeah, the molar mass of this was exactly the same as the 791.0102. So that would just be numerical formula. So I lost 2 marks there for the last 2 steps, the multiplying, and for here, everything else was correct. And then, my explanation for random error was a bit lackluster, so I knocked myself a mark there. In the marking key, it said this is so long. It was random error is fluctuations in data due to limitations in the measurement device or technique, which are unpredictable and to varying extents and do not have a sway on the direction of the data. Oh my god. Unpredictable and happen to varying extents. I think that's the one that I'll be using, and maybe I'll say due to limitations in measurement. another thing they also talked about, but that I didn't, but it was like a small part of the big marking key. So I didn't knock myself a mark for not including a systematic error, because systematic error was exactly something like this, and then at the end it was like, oh, direction. Yeah, back. Anyway, they were talking about systematic error would skew the data in a certain direction, but random error wouldn't. So that's just another thing I can add for future exams. It's all good. I think the rest from here was pretty good. Oh yeah, for minimum, you needed to use the maximum mass of cadmium, which, oh my god. I assume they should have worded this better and said the minimum mass to guarantee you're going to remove all the cadmium 2 ions. Because if the uncertainty is that, then I can just take the lowest amount, and then use that as my minimum. Like, brother. Because, I mean, that could be the minimum mass of sodium phosphate. So I knocked myself 1 mark, but then the rest was good, so 7 marks of follow through, I guess. God. That was so annoying to see. I think that's totally just bad wording. I guess maybe here it says needed to, but should have said guaranteed. Guaranteed that you remove all of it. So yeah, 1 mark off there. Yeah, my explanation was fine. My diagram was just not. You got 2 marks for doing a Boltzmann diagram. No, I said I didn't, so I knocked myself 2 marks there. The actual one that they use for the marking key has been blocked off due to copyright, I think. Let me find it. What question are we up to? 37. 37, yeah. It's blocked off for copyright, so I don't know what it looks like, but I assume this is something like what it looks like. Here I got 1 mark off because you were supposed to make it go to the same final concentration. Just kind of annoying. I guess that HCl wasn't limiting, but I did get 1 for a steeper gradient. But here, reactants, steeper gradient, and the reaction finishes faster, which is fine. I said reaches final percent extracted sooner, but same thing. But I just put here a little note that the marking key just said that the reaction finishes faster. Down 6 marks. Oh yeah, I maybe could have been, again, this was in brackets for the marking key. So I was like, I won't knock myself a mark. But it did say it was too costly due to energy or equipment costs. And then the mark I lost was that I didn't talk about the catalyst. I remember looking at the catalyst and thinking, okay, I'm going to write about the catalyst. And then I just didn't, so yeah. 5 marks there. Full marks here. Full marks here. Yeah, peptide bonds, apparently, or at least in this exam, you could have circled the full CN like that. Or you could have even circled the full thing like that. Which, I mean, I think that's changed. So I'm pretty sure you can only circle the literal bond now, but I'm not sure. Yeah, I could have just done it a bit condensed instead of having to draw all the atoms. It says show all hydrogen atoms in full structural formula though, so yeah. But whatever. Still gave myself the mark. Here I gave myself a mark for saying that leucine can act as a Zwitter ion. However, there was 2 marks I lost, which was these 2. And then I should have probably also talked about NH3 plus and COO for each of them as well. And then since in acidic conditions the COO is basic, it'll accept a proton. And then in basic conditions the NH3 plus is acidic, so it will donate a proton and it will get deprotonated. So I lost 2 marks for the acidic and basic because I just didn't talk about the CO and NH3 plus. Here I got, I was actually scammed here. I thought it might have been this because MET has a sulfur, but apparently disulfide bonds can only form between cysteine, so I got 0 marks. So yeah, you just had to talk about cysteine. Pull it up. You have to talk about cis and cis. You could have also just circled it up here. Oh. Then you have to talk about how cis and cis have disulfide bonds or bridges, which are covalent bonds. And these covalent bonds are much stronger than other forces and other intermolecular forces present between the other pairs. I've got one. No, I don't think I can get one. Yeah, because I didn't specifically say that the cross-linking or the disulfide bond has stronger forces of attraction than the others. So I'll say here disulfide bond has stronger forces of attraction than present in other pairs. Okay, and then going down, I think from here was pretty good. I think for this one, it's just the equation, but it gave it as an ionic equation. But I thought it doesn't specifically say ionic, so I'm gonna give myself the full 2 marks. However, in the future, I think I'm just gonna default to ionic equation. And then here was fine as well. Oh yeah, they just said diluted instead of saying the concentration decreases, but I mean they're literally the same thing. So yeah, 89.4%. But you know, I'm fine with. I'm not particularly happy about it. I want it to go up a bit. But yeah, let's check the summary examination. The max for this exam was 95.2, and it looks like maybe I would be in the top 50 candidates if I got an 89 in this exam. So yeah, 50 divided by, and there were 4,965 that did it. So I've been in top 1%, which is good. Right at the ATAR 99 standard. So yeah, I would like this to go up. I lost so many marks in extended response. I totally could have got the cysteine one, which would have gave me 3 marks. Which would have gave me 72 divided by 79 times 35 plus 84 divided by 94 times 40. Oh, 90.6. Ah. Oh, I wish. Oh, well, that's right. We go next. Next is physics. Let's go.